Hello, today we're going to look at terminal velocity, and then within the video we'll look at what that means, what are the forces, and then also how we can use it to understand some graphs. This video follows on from the distance time graph video, so if you haven't yet watched that, I strongly recommend doing so first. Quick reminder of what you're going to need today. So as ever, you will need a piece of paper, a pen, a pencil, ruler, and rubber. You will ideally need a scientific calculator, although a phone calculator will do if it absolutely has to. And of course, you need to bring along your thinking brain. So hopefully you've got all those and you're ready to move on with the rest of the video. So before we begin, let's just draw 6 boxes and then within them write down everything that you can remember about terminal velocity. I've started us off, so the first thing that I thought of was that velocity is measured in meters per second. So now over to you, and when you're ready, press play again, and then we'll look at some of the possible options that you may have come up with. So here are mine. So I've got the equation, velocity equals distance divided by time, or speed equals distance divided by time. I remembered that terminal velocity is the maximum velocity or the maximum speed that something can get to. An example I thought of was a parachutist, so someone jumping out of an aeroplane. And I remembered something about forces, and that when you're at terminal velocity, the forces are balanced, and then the resultant, the overall force, was 0 newtons. But let's explore some of this in a bit more detail. So the sort of question of why should I care about this? Well, world records. There was a person called Felix. You may and may not have heard of him, but he recorded the highest parachute jump in the world. He went up into space, jumped out of a hot air balloon, and if you want some more information, the website is just there, so bit.ly/terminal velocity Felix. Another reason, it's the maximum speed that you can get to. So that might be you in a car, it might be you running, it might be you swimming, it could be absolutely anything. Everything has a maximum speed that it can possibly reach. And it's different in space. So because space doesn't have air, in fact, it's a vacuum, nothing's going to get in the way. So things do tend to move a lot easier in space because you don't get that air resistance. Just like when you walk through water, that's a lot harder because you've got the fluid in the way, and that's going to limit how fast you can go. It's going to limit your maximum speed. You may have heard of the hammer and feather experiment on the moon. It's well worth looking on YouTube, but the picture quality isn't great, so I've just got this picture instead. But we've got an astronaut letting go of a hammer and a feather. Now on Earth, the hammer would land a lot faster and sooner than the feather because the feather reaches a terminal velocity a lot sooner, so it doesn't move as fast through the air, whereas the hammer carries on accelerating. The feather is caught by the air, or the air catches it, so the air resistance with the feather is a lot greater. Whereas on the moon, when they were dropped, they fell at the same rate, and that's because the gravitational pull of the moon was the same on both objects, and the force pushing it up, well, there wasn't any because there was no air resistance, so they fell at the same rate. A similar example is what you can do at home that doesn't involve a hammer and therefore is slightly safer. If you get 2 pieces of paper that are the same size, screw one up and drop both pieces of paper at the same time, so a screwed up ball and also a flat piece of paper. And although they're the same mass, the screwed up ball of paper will always land first because it's got less air resistance. There's less drag. So this one, because it's got a larger surface area, has a higher drag or higher air resistance, and as a consequence will reach terminal velocity before this one. So this one will carry on accelerating for longer, whereas this one will just go down to the ground. So it's quite useful thinking about an example with terminal velocity, and that is a parachutist. So let's start thinking about how that then can be applied to terminal velocity. But just before we do, in the last video we looked at distance time graphs, and this line, you'll recall, tells us that it's a constant speed. The distance is increasing at the same rate, it's a straight line, so constant velocity or constant speed. However, for velocity time graphs, which we can then apply to terminal velocity, we need to make sure we don't have a distance time graph, but we have a velocity time graph. So this graph actually tells us something slightly different. Have a think about what this does show us. And when you're ready, press play and I'll quickly go through the answer. Okay, so I've just added some numbers to the velocity axes. And hopefully what you can appreciate is over time, the velocity starts at 20, later on goes to 40, later on goes to 60, to 80, to 100, etc. In other words, the velocity is increasing. The object is getting faster. And if something gets faster with respect to time, so change in velocity divided by time, that gives us an acceleration. The object is speeding up. So just to be clear before we move on, a distance time graph, which was the previous video, that shape graph would give us a constant speed or velocity. But in this video, this is now a velocity time graph, and that tells us that we've got an increasing velocity, or we would say a constant acceleration. Another comparison to make between a distance time graph and a velocity time graph is the horizontal straight line. So think about the difference. What does that line tell us? So what does that line tell us if it was a distance time graph? And what does it tell us for now when we're looking at a velocity time graph? So again, when ready, press play. So like previously, I've just whacked some numbers on the y-axis. And what we can hopefully now see is as time ticks forwards, the object remains at 100 meters per second. If this was a distance time graph and we remained at 100 meters, that would mean we're not moving. But because it's a velocity time graph, this tells us we're staying at the same speed. So I'll just write on some notes just here to be clear. If this were a distance time graph, this would be stationary, so posh word for not moving. And the graph that you are looking at is a velocity time graph, and that tells us it's a constant speed or constant velocity. And it's important that you do look at the axes just to be clear with the sort of explanation or description you need to show the examiner. Okay, so now it's time to look at the sort of graph that you'd expect to see of a parachutist jumping out of an aeroplane. So I'm going to ask you to press pause again in a moment, and I'd like you to look at the different sections of the graph to try and work out what on earth is going on. So this will be the first section just here, so that'll be section 1. We've then got a second section just here, which can be section 2, and section 3 will be this part just here, section 4, this part, section 5, this part, and we can blend that in just there to section 6 as well. So have a little think about what's going on, thinking about the velocity, the speed at which the object is going, and what the graph is representing as the parachutist falls out of his aeroplane. Hopefully you've given that a go. Let's now focus on just section 1 and a little bit of what's going on for section 2. So I've highlighted a bit of the section of the graph that we need to focus on. So I'm drawing an aeroplane, and out of the aeroplane I'm going to draw the same person falling over time. So it's falling closer to the earth. Now, to start with, the force on him pulling down is always going to be the same. So the force down is the person's weight, the force due to gravity, mass times gravitational field strength. But to start with, he's not moving very fast, so the air resistance is quite small. But as he gets faster, as more particles hit him or her per second, the air resistance gets larger and larger and larger. So that then means that over time, the forces become balanced, just because the downwards force is equal to the upwards force. So the up arrow size is the same size as the down arrow size down there. So the net force, or the resultant force, the overall force, we would call 0 newtons. The forces are now balanced. So what's a good idea to do now is to relate that to the parts of the graph. So to start with, just here, the velocity is increasing really quickly. And that's because the downward force is a lot larger than the upward force. As time goes on, this is starting to flatten out. And that's because the weight is staying the same, but the air resistance is getting larger as the object moves faster and more air particles are hitting it per second. And then as it gets faster again, it balances out so that the line is almost nearly flat. And it gets to the stage here where the upward and the downward forces are equal to each other, so the velocity stays constant. The object has reached terminal velocity. It cannot get any faster. The weight pulling down is equal to the air resistance pushing up. So let's now focus on these two parts of the diagram next. But if we just quickly remind ourselves, the person has got faster, 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 faster. The rate at which they get faster is getting less because of the air resistance building up, and eventually the weight pulling down equals the air resistance going up. But they're getting close to the earth, so they need to do something in order to save their life. So what they do is they open up their parachute. So here is our person, and they're just opening up their parachute. And all of a sudden, they will lose a huge amount of speed. They will go from moving really fast to moving really slow. And that's because the air resistance has got so much bigger really quickly. But then as they slow down, we then have the red arrow, the air resistance gets smaller and smaller. And then it gets to the point where they're going a lot slower, so the air resistance then balances out with the weight going down. So to start with, in the black arrow at the top, as soon as they open the parachute, we get a huge shift in air resistance, huge increase in air resistance. And as they slow down, and it happens really quickly, the air resistance gets less and then gets less again until we have another terminal velocity, which is this part just here, when the air resistance is the same size as the weight. The difference, of course, is this terminal velocity is a lot less than the original terminal velocity. They're moving at a lot less velocity. So to be clear, this part is where there's no parachute open, so they reach a much faster terminal velocity, there's much less air resistance. And this second part is when the parachute is open, when the air resistance is a lot greater, so the maximum speed, the terminal velocity, is a lot less. And then the final part is when they land. And you'll notice the line that goes along the bottom, that tells us that there's no velocity. And that's why there's a steep line just here, because when they land it's quite quick, they just land. So their velocity goes from something to nothing really, really quickly. My next thought for you to have a think about is which of these three people would have a greater terminal velocity. Let's assume that each of the parachutes is the same, and we have the lightest person just here, the heaviest person just there, and the one in the middle in the middle. So have a think, which one of these three people would reach a higher terminal velocity? In other words, which one would be falling to the ground fastest? Assuming these are all the same. Okay, I hope you've given that some thought. So let's look at the weight first of all. So this person will have the lowest value, so the shortest arrow. This one will have a slightly longer one. And this person will have the longest arrow for weight. Now, when they're falling, to start with, the air resistance will be the same, and they're going to carry on accelerating down. But over time, the arrow will get bigger and bigger. As soon as this person here reaches terminal velocity, when they're the same size, that will stop that person getting any faster. Whereas these two, the arrows will carry on until, again, this one reaches terminal velocity when the arrows are the same size. But our heavier person, that can carry on for a little bit longer. So that means the person's accelerating, getting faster for longer, but eventually they will reach terminal velocity. But because this one has accelerated for the longest amount of time, it's sped up for the longest amount of time, this one will have the greatest terminal velocity. And this person here, because they accelerated for the shortest amount of time, they will have a terminal velocity, yes, but it will be a lot less than our heavier person. Into our final example, and that would be of a car, because a car can reach terminal velocity as well. So the reason a car moves is because of its engine, and that's going to allow the car to go forward. So we can put that as the engine force. Now, we've got air resistance going backwards, but we've also got some other resistive forces that are happening. We've got some friction as well, and that's going to obviously slow the car down too. But to start with, when you're accelerating, maybe it's some traffic lights, then because the two forces are very different in size, the car can accelerate forwards easily. But again, just like with the parachute going down to the ground, as it gets faster, it's hitting more air particles per second, so the rate at which it can speed up gets less. So with a car, as it accelerates forwards, more air particles will hit it, and the consequence of that, as it gets faster, the air resistance will get greater. And then it reaches a point where you're going a certain speed, the maximum speed that the engine can push you forwards at, and that's going to be balanced out with the air resistance and the friction. And at that point, when the forward force from the engine equals the backward force caused by the air resistance and the friction, that's when you've got balanced forces and you've got a resultant force of 0 newtons. That doesn't mean the object stopped, it just means it's no longer changing velocity, it's moving at a constant speed. So out of these 4 diagrams, A, B, C and D, only one of them will be a balanced force. Can you tell which one that is? Is it A, B, C or D? Okay, hopefully you got the right answer. The only balanced force is this one. And of course, for something to be balanced, that means that it's moving at a constant velocity or constant speed, or is not moving. That means the other 3 must be unbalanced, and that's because the arrows are of different size. And when you have unbalanced forces, that's when the object is able to speed up or slow down, so accelerate or decelerate, so you get a change in velocity. Balanced forces will always have 0 newtons as the resultant force, whereas if it's unbalanced, they will always have a value greater than 0 newtons. There will always be a force, and then that then links to the topic of F equals ma. So where there's a force, there's an acceleration. So just before we go, as ever, if you can review what you have learned, so draw out your 6 boxes or add to the ones that you wrote earlier. So one of mine might be that a higher air resistance will make something have a lower terminal velocity. So something that has a lot of drag, that will then stop them from going as fast. That's why racing cars, for example, they're really aerodynamic because they want to reduce how much air resistance that they have